Anna, thanks. It is time for our chemistry lesson this morning with excuse me, with Mr. Jesse Miller. That's you, right?
Yeah, I thought there was somebody else here.
No,
That's
yeah,
right.
just, how you doing?
I'm doing great.
Good.
How are we?
Well, now that I got through that intro, I'm doing just fine.
Okay.
All right, so we're going to talk about something that's pretty common, right? Cold packs?
Cold packs and heat packs in the second segment. We'll talk about, like hand warmers and things like that. I thought it was appropriate. This kind of, actually, I read one of your Facebook posts talking about scraping a windshield, and I thought, hey, I can talk about cold and hot stuff.
Yeah.
So,
there we go. Look at that.
Yes, you were my muse. So,
thanks, Justin.
I don't know where to go with that. All right, so
no one does.
So we're talking about cold packs. Now, a lot of times, cold packs, people just take, they'll have the freezer packs. You throw it in the freezer, it gets cold, then you take it out and you put it on there. But there's the portable type, which is the kind I'm going to talk about, which aren't cold, and you don't have a freezer handy, and you're out in the field or whatever, and you'll see them, they'll break it up, and they'll mix it up, and all of a sudden it gets cold.
Right.
Those are the kind of cold packs we're going to talk about. And there's actually a chemical reaction taking place in there. Now, in thermodynamics, and I know we don't have a lot of time thermodynamics can take hours to talk about, and we do in our classes, but in a nutshell, you have exothermic and you have endothermic reactions. Exo meaning outside, endo meaning inside. So in an exothermic reaction, it gives off heat, like the hydrogen balloon that blew up and gave lots of flame. That would be an example of an exothermic reaction. It gives off excess heat. And an endothermic reaction, you have to put heat into the system in order to get the reaction to be what we call spontaneous.
Okay.
Okay. So a lot of times when you mix something together and it's a spontaneous reaction, but it's endothermic, it pulls heat from whatever source is on the outside, in this case, you or the air or whatever. So I have two chemicals here. This is barium hydroxide, octahydrate, and this is ammonium thiocyanate. Okay? I know it doesn't mean a lot to you.
Sure.
But they're two different salts. When I mix these two together, and they're two solids, and this is kind of an interesting reaction because what we're going to do is we're going to take two solids.
Something going to happen?
It's not going to explode, I promise. I would warn you, right? We're going to take two solids and we're going to mix them together, and it's going to form a liquid, basically, and some gas. You'll smell some ammonia coming off here. And when it does that, this is an endothermic reaction, and we'll put a little water here on the bottom of the beaker so we can see how cold this really does get. And as this goes on, it's going to get cold, and I'm going to talk a little bit.
So it's getting kind of slushy now.
It's getting slushy because that reaction is taking place, and we're getting barium thiocyanate, basically ammonia and water out of this. And it's endothermic, so it's going to get cold, and I'm not going to be able to hold it here in a minute. So we'll let this go. Now, the reason why this gets cold and it's still a spontaneous reaction, the energy of your system has to be, we're going to let that sit for a second, the energy of the system has to be lower at the end than what you started with. Think of a ball rolling down a hill. It has a lot of potential energy up here, it has very little potential energy down here, right? Otherwise it wouldn't go. You can't roll a ball uphill unless you throw a lot of energy into it. So these reactions, chemical reactions are the same place. They go from high energy to low energy, and that's what we call spontaneous. If it's spontaneous, it will go. Usually it gives off heat because it has extra energy. But in the case of an endothermic reaction, it has to take heat in. So something else is going on to make that energy lower, and that is what we call a change in entropy. There's a change in entropy. Now, entropy is another one of these things that people don't want to talk about because it's very difficult to explain. But if you think of entropy as a 2-year-old, okay, when you have them in its playpen.
So I typically think of it.
You got your 2-year-old in the playpen, they're constrained. They're not going anywhere, right? They have very few degrees of freedom to go.
Right.
You let them out of the playpen, they can go lots of different places and cause havoc everywhere. And their entropy would increase. The entropy of the system increases. The random disorder, as a lot of people like to call it, but it's not really true. It's not really right. Okay, so this is getting very cold, and as you can see, it's now frozen to the bottom of the wood block here.
Can I touch the beaker?
You can, but be careful because you could get frostbite. Well, you can touch it longer than that.
Oh, it is cold.
Yeah, just don't put your tongue to it. All right,
cold.
You didn't happen to have a cup of warm water, would you?
In this case, it's taking heat around from its surroundings, in this case the water that I put on the bottom, and it's frozen. It gets down to about minus 20 degrees centigrade.
Yeah, because that's
cold.
frozen. I mean, that's solid.
It really is. And you can smell the ammonia coming off of here a little bit. And the reason why this is a spontaneous reaction, even though it takes heat to make it work, is because the entropy is increasing, and the entropy offsets the enthalpy, or the heat of formation. So
there's going to be a
it's going from a solid. It's going from two solids into a liquid and a gas. And as you can imagine, a solid is very constrained, whereas a liquid kind of is able to move around a lot more freely, and a gas can move even more freely. So its entropy, its degrees of freedom, its ability to move, so to speak, is increased.
Okay.
And that's the reason why this reaction works. Now, it's a lot of chemistry for something you just go like this and you put it on there and it's cold.
Right.
But it is important, and there's not a lot of these reactions that you come in contact with every day. There's a few of them out there, but this is one of the classic ones just to show. And as I can say, it gets very cold.
Very cool.
It just froze that block right to the bottom of the beaker.
What will you think of next? Probably warm packs, because
Warm
that's what we're
packs,
talking
that's
about
what
at
we're
7
talking about
o'clock.
next. And entropy comes into that as well.
All right.
I need more entropy in this relationship. Feeling confined.
I'm thinking there's a lot of entropy going on right now.
More of the morning show after this.